I'm logging into ResponseWare now to get the session ID. It's randomly choosing. There it is. 20. There's our question, open polling. So those that sign in faster, you can start answering. All right. I think you guys are getting the hang of it after just one already, but here's the channel ID and session ID, so you guys can sign in. And I won't lie, I'm hoping this is an easy one, but I'm checking this question. A 2 kilogram melon, so what's the force of gravity acting on it? Lest I'm overlooking something and half of you miss it. I don't know, we'll see. Looks like most of you responded. Getting there. Ten, 9, 8, 7, 6, 5. Everybody had a chance to log in? 3. Did yours say channel 41? Yeah. All right, you just hit like A, those black buttons, or B, or whatever it is. I'm just.
But you don't have to have anything on your screen?
Nope. Yeah, hit a button. Let's see. Yeah, so say you think it's A. It gives you a check mark and says, yeah, I like it. If you want to change it, just hit a different button. That's to save battery power, so it's not always displaying. I believe. 5, 4, 3, 2, 1. All right, overwhelming answer C, which is correct. Good. That makes me feel better. But, of course, for the 2/3 that didn't, from our homework mostly, the force of gravity. How do we find that? Yeah, ma. That is Newton's second law. And what is the acceleration in this case? It's gravity. So that is, and we'll just say 10 for the moment. 10. So what was the mass? 2 kilograms? And this one where, what are the units? Well, I use standard units, so it should be the standard unit for force that we've learned is I heard somebody say it, a Newton, which is the same thing as a kilogram meter per second per second. But that happens enough, and in honor of Sir Isaac Newton, we call it a Newton. So that's the weight. And I want to emphasize again, that's a force. Our weight is a force. This is the mass. They're not the same thing. Mass and force are different. A lot of people still get confused. Questions? All right, let's try another one. Go. Yes, I realize I haven't gone over this explicitly, more implied. So I wanted to see what you guys got and who's been reading the chapter. I thought there'd be more responses by now. I'll give you a clue. What's directly proportional mean? Any takers? One affects the other. Yeah, that's proportional. Yes, if it's directly proportional, If one changes, how does the other change? The same. Good. So inversely proportional? If one changes, the other changes the opposite way. If that helps you. So you know what they mean. All right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Oh, we're split there. It's either A or B, right? All right. For a given force, acceleration and mass are. I'll give you another clue. I'm going to rearrange that. These are guides to our thinking. For me, if they're on the same side, well, I'll do it both because it might help you one. Some might see it better this way, some might see it the other way. So I'm going to write it like this. Do you see how I got to that? This is the minimum algebra I'm hoping you guys got, but since we're still at the beginning of the semester, let me know if I confused you. Okay. So here, if you increase the mass, what happens to the acceleration? Mathematically, if you make the denominator bigger, you're not instilling confidence. I don't know. I can't tell if you're just not answering and hoping somebody else will, or you're actually confused. Let's do an example then. Let's say it was 1 over 2. If we increase the bottom number to 1 over 4, did we just make the thing bigger or smaller? Smaller. So if we increase the denominator, the acceleration decreases. Is that directly or indirectly proportional? Yeah, inversely. So that's the correct response. Another way to look at it here, if this has to remain constant, the force, and you increase the mass, the acceleration would have to be less to keep this the same. Now think of it conceptually. Inertia is a property of matter. It's based on how much mass they are. It's a way of measuring. So if something has more mass, it has more inertia, resistance to wanting to change its motion. So for the same force acting on it, if you increase its mass, increase its inertia, increase its resistance, it won't accelerate as much. So its acceleration will be less. In other words, it's harder to move the more massive it is. So they're inversely proportional. Maybe one of those 3 ways will help you. All right, one more. Go. Hopefully all that will prepare you for this one. It's basically the same type of question, but we're changing 2 things. Asking what happens to the third. And I suggest if you can't reason this one in your head conceptually yet, write it down. They change by a factor of 2. So plug that in and see what happens. That might help some of you. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Bang. Hey, we got the largest majority of C. Very good. So a cart is pushed and undergoes a certain acceleration. We got this again. Certain acceleration. If it's pushed with twice the force, so if we make this 2F, while its mass doubles 2m, what's that acceleration going to have to do to keep that equation equal? It stays the same, because there's a 2, makes up for that 2. For the last question, if you doubled the mass, it's going to have twice the inertia. So it will require twice the force to give it the same acceleration. Does that make sense? Force and mass, we would say, are directly proportional. You double the mass, you double the force required to maintain that same acceleration. Questions? I like these just to emphasize as we continue in this semester that equations are guides to thinking. That just shows the relationships between those variables and how they're proportional to one another, directly or inversely. And some people rely on this because they're better mathematically trying to understand things, and that's okay. If plugging things into there helps you figure things out, awesome, that's what it's for. But how it came about was conceptually they realized this stuff. We've talked about plenty now what acceleration is. You realize we have 2 ways to define it now? What's one? Okay. It is a change in velocity with time. It's the rate of change. Gravity is 10 meters per second, so it's how fast we change our velocity. Now we have a second way. We've already written it on the board. Yeah. Force divided by mass. They both give the same thing, but there's 2 ways of looking at it, which can help us. Again, let's make sense of how they came up with this. We did this one. If you have more mass, you have more inertia. So for the same force, more mass, it won't accelerate as much. I think you knew this. Scientists observed this and noticed that relationship. It's inversely proportional. A is proportional to 1 over m. They learned that first. And then like this one, they learned if you double the mass, you double the force. So the acceleration is directly proportional to force. They just combined these 2 to get this equation. And in my mind, as much as people love to say this is Newton's second law, which it is, I like to think of it this way. It's the same thing. But it helps me remember that relationship, the proportionality. Because that's kind of how it conceptually came about. Your book defines, I like this. This is, see if you catch on to this. Your book defines Newton's second law of motion as this. The acceleration of an object is directly proportional to the net force acting on the object, is in the direction of the net force, and is inversely proportional to the mass of the object. Okay, until before right now, and maybe some of you still are, who felt like, basically all they did was explain what we just said, summed up by this. The acceleration of an object is directly proportional to the net force acting on the object. Is in the direction of the net force. That's just reminding us that these are vectors, and the direction matters. If you push it to the right, it'll accelerate to the right. And is inversely proportional to the mass of the object. So a lot of words summed up by this nice little shortcut. That's why I like equations. You can say the same thing in less time. So I hope they don't scare you this semester. That's my point. Okay. Let's do this demo. I always like when you can use dart guns, toys in general, in a physics class. And of course, since they are toys, they're a little cheap. All right. So basically, I compressed a spring. We haven't got to energy yet, but most of you realize I stored some energy in here. When I pull the trigger, it'll release the energy, and the spring will push on the dart. A force is exerted on a mass and will cause it to accelerate, speed up, change its velocity. Now, same type of gun, same type of spring. I just have a dart with a piece of clay on it. Thanks. I'm going to shoot it. You guys can probably figure this one out. What'll happen? Won't go as far? It's got more mass. It's heavier. So your reasoning process is just why, because it's heavier, follow that through to why it wouldn't go as far. It won't go as fast. Okay, that means it's not going to change its velocity as much. Why? Force of gravity acts on this one? Does it act on this one? So why does that matter? It's acting on both of them. Mass. The mass is bigger. Okay, why does that matter? That's from Newton's second law. And go back to Newton's first law. Why does more mass cause it to not accelerate as fast? It doesn't want to move. It wants to stay where it's at. We call that inertia. So now you've completely justified why it doesn't go as far. We'll do it. I'll shoot it up so you can all see. Ready? Yeah. Not near as far. So, in scientists, and what I'm encouraging you through this course, on your homework when you explain things, and definitely on your paper at the end when you're trying to justify your superhero, some statements like, it won't go as far, is a description. It's not an explanation. Why won't it go as far? Because it's heavier. Okay, you're getting closer. Why does being heavier mean it won't go as far? You got to get back to some laws and say, because that's the relationship, and it has more mass, so it'll resist that change in motion and won't get up to as high a speed. Does that make sense? So start getting in the habit of thinking through and reasoning, and I think you guys will be very pleased with your outcome this semester. A lot of these questions you probably realized on the homework, and they're the same for the exams. You can't just memorize an answer. Right? Oh, which one will go farther? Oh, that's right. We learned that. It was the clay one. Because I'll change up the question. But if you can reason through it and understand the logic, you'll be able to relate to problems the rest of your life. Anyway, there's that. I want to show this demonstration. So I'm going to hang this lead ball from a little string here. And I'm going to tie, this is a safety string. So if this breaks, it doesn't hit my finger. This one's a little, what am I doing? That's not right. There we go. Because I'm going to pull on this. And with if it only had this attached, it only makes it to there. So if my hand's down here, it won't hurt me. But this white string is what's holding it up right now. This is just extra. So there's tension in this string. How could we figure out how much tension is in that string? It's the support force in this case. It's what's holding it up. How would we figure that out? The weight of the ball. Yeah, and how do we figure weight? we'd have to know its mass. And we know that the acceleration right now on it, due to the Earth pulling on it, is 10, 9.8 meters per second per second. So yeah, we'd get its weight down. And what you know is you draw that force body diagram. So there's its weight, mg. But the net force is what right now? 0, very good. Which means what? Something's pulling the other way, equal and opposite. That's that support force, the string. So that's the tension in the string, because those are equal. It also tells us that this is not accelerating, because if F is 0, A has to be 0. The net acceleration. Gravity is still trying to accelerate it down. That's 9.8. We didn't get rid of gravity. Poof. But the net acceleration on the object, which means it's not changing its velocity. Okay. What I'm going to do is I'm going to pull on this bottom string. I'm going to add another force down. So if you draw it, F pull maybe. And I can vary that. I can make it smaller or bigger. What do you think will happen? I'll give you a I'm pulling on it right now a little bit. So it essentially looks like that. But what changed? If I pull on it, what has to change in this picture? Oh, good, very good. Because I now have, not only do I have the weight, I have this down. So it's F weight down plus F pull down minus the support force up. That's the total. And since it hadn't moved yet, that has to be 0. You can rearrange that and see that this has to be balanced by that. So I've increased the tension in the string, right? The top string. If I pull even harder, at some point the tension will break, right? The string won't be able to handle it. Think I can do that? There. So I just kept increasing this force of pull, got bigger and bigger and bigger, so that was trying to get bigger to support it until the string couldn't handle it anymore and it broke. You with me? Is there any way possible, let's set it up again, that I can break the bottom string? There, we got a new string, got this one. Is there any way I can pull on this? Oh, we got a thought. Oh, the tablecloth pull? Very good. This wants to stay where it's at because of inertia. So let's see. If I yank on this fast enough, it's like the silverware in the plate. They want to stay put. And it's almost like this would not have time to react. Well. Yeah. So I was still adding this, but time is a factor too. We're going to play more with that as the semester goes along. But the emphasis here, I'm hoping, the reason I'm showing you this is the difference between weight and mass. The weight right now puts tension in here. And I can add to that by pulling down on it. So that increases. But if you do it quickly enough, the only thing you're actually trying to overcome is its inertia. And that's why this string breaks. How do you weigh somebody in space? They try to figure out, astronauts need to keep track of if they're getting fatter or skinnier. Can they go step on a bathroom scale? Why would that not work? There's no force acting on, no force due to what? Yeah, we usually see them floating around. They look weightless, right? So if you just step on a scale, you're measuring weightlessness. I do want to say right now, it is a misconception. Astronauts in space, there is gravity. A lot of gravity, actually. They're just constantly in free fall. We haven't got to orbits. But it's kind of like shooting a cannonball. You know, you shoot it out, and it falls because gravity pulls it down. What if you shot it faster? What would happen? Yeah, it would go further before it hit the ground. What if you did it even faster? Even further. What if you did it fast enough that as it's falling, the Earth, the surface of the Earth, because we know it's round, curved out from underneath it? It's constantly falling, but it would never hit the Earth, the ground. It would go into orbit. That's what astronauts are doing. They're in orbit. They still feel gravity. But if they step on a scale, they feel weightless. So what hasn't changed? What's still the same about the astronaut? The mass. So you can't just step on a scale and weigh an astronaut. Got any ideas how they might weigh them then? Or at least maybe they don't weigh them. They calculate their mass. How could we do that? At least conceptually. Maybe not practically, but how do you measure mass? Oh, tape measures the volume, how much matter they actually have. Might be hard to guess density, though, but yeah, that could work. I mean, it's physically, you know, if you saw me like this, you'd assume I got more mass. Yeah, that's true. They use this concept of inertia. Picture this. How many of you can push a car? Let's say you put it in neutral. You all help somebody. Is it easy, though? No, of course not. It's still kind of hard, but you could do it. Well, maybe a lot of you probably. But it's not easy. And that's because it has a lot of mass. Do you have to push on it with the same force that it weighs? Could you lift a car? Can anybody lift a car? No, my hand's down. No, I can't either. It weighs a lot more. But because of wheels, we can eliminate a lot of friction, and we can at least push it. When we push it, we're not overcoming its weight. We're overcoming its inertia and some friction. So if you took a car to the moon, where there's less gravity, 1/6 the amount of gravity than as it is here, and put it on a scale, yes, it would weigh 1/6. But it would. Do you think it would be harder or easier to push on the moon? Are you at least thinking in your brain? I heard a few answers. Did its mass change? Did its inertia change? So it should be require the same force to get it moving. Does that make sense? If you put it on a scale, the scale would read less because it's being accelerated down by the moon with less force. But it still has the same mass, so it still resists you trying to change its motion, exactly the same as if you were here on Earth. Now there is a greater normal force, and if you throw friction into there, it might be a little easier. But the idea is you can take an astronaut in. They'll sit in a chair, one way they do it, that's clamped off with like some springs or something. And they just try to oscillate them, kind of like this, springing back and forth. And they can measure the frequency that they bounce back and forth. If they go fast, then they have less inertia. They're resisting the change less. It means they have less mass. And so they can go faster for the same spring force trying to bring them back. But now picture it. You put this big old fat astronaut, which doesn't happen, in there. What do you think? It'll be a little more sluggish. Whoa, whoa, whoa. The frequency will be less, and they can determine, he has more mass. And they can figure out exactly how much. But it's because they're going against the inertia. I think that was clever. So they can, given back here on the surface of Earth, plug in the acceleration due to gravity and say how much they weigh, how much they've changed. Here's another way to do it. If I just have a string, I can pull slowly on this 13-pound lead brick, overcome some static friction, hopefully, and it starts moving. A lot of force in the string. But if I just yank it, it breaks. Because its inertia wants to keep it put. And the string couldn't handle that initial jolt. So I never want you guys to forget that there's an obvious difference between force and mass. Weight, which is a force, and mass. All right. The pre-lecture questions. A cart is pushed and undergoes a certain acceleration. If the force is held constant, then the mass of the cart doubles. So it's this one. We just doubled the mass. If the force is held constant and the mass doubles, what will its acceleration do? Hopefully that's more obvious to you now. If this goes up by 2, this must go down by 2 to keep the force constant. So it's half. The acceleration would be half. Conceptually, it's got twice the mass, twice the inertia. It's going to resist twice as much, so it won't accelerate twice as much. It will accelerate half as much. The second one was use Newton's second law to answer this question. Ignoring air resistance, the acceleration of a vertically thrown ball at the top of its path is what? So that's this game again. You throw this up right there at the top, right there. What's its acceleration? Okay, we had 2 votes for 10. Is it moving at the top? Is something changing? What? It's velocity. And if you have a change in velocity, you must have change in acceleration. And we know in order to accelerate something and make that change, you must apply a force. What is that force? Yeah, it's weight, gravity. The Earth's pulling down on it. It's causing it to accelerate. So even at the top, when it's not moving, it is being accelerated at 10 meters per second per second. Let's ask you this one. Which one of these do you think weighs more? You're right, basketball. Can we figure it out? Let's see. This is, I wrote on it, 597 grams. So what's its weight? We'll round up. 600 grams. How many kilograms is that? 0.6 kilograms, because there's 1,000 grams in a kilogram. So we change it by a factor of 1,000. That's its mass. So what's its weight? There you go. Multiply that by the acceleration due to gravity, 10. And yeah, you get 6 newtons. All right, the tennis ball says it's 57 grams. We'll call it 60. So that's how many kilograms? 0.06 kilograms. So its weight is 0.6 newtons. So their weight differs by a factor of 10 in this case. So this is heavier. It's got more mass. So which one does the Earth pull on more? They're pulled the same? So the Earth exerts an equal force on both of them. The force of gravity is the same? Okay, he made an observation. The 10's the same for both of these. Excuse me. I'm trying to be a little sneaky to help you guys come to the realization. The accelerations are the same. Do you agree with that one? Okay, you seem happier. Yeah, these are both being accelerated down at the same rate, 10 meters per second per second. But who has more mass? So we go back to this relationship. If the basketball has 10 times the mass, but is being accelerated at the same rate, how much more force does he feel? 10 times. That's why he's 10 times as heavy. This is heavier. The Earth is pulling it down on this with 10 times the force. So the force of gravity is not the same. It's a very common misconception with, I would say, 98% of the world's population, including those that are in a physics class, so don't feel bad. That's why I'm bringing it up. The force is not the same on these. The acceleration due to gravity is the same. And it's all because of, well, wait, if this is going to accelerate at the same rate this one is, and it's 10 times as massive, we have to pull on it with 10 times as much force to have the same effect. And that's why, what you know, all objects fall at the same rate. They hit the ground at the same time. Galileo did an experiment and figured this out. That's because of what we just said. But remember, it's not because the force of gravity is the same. It's not. This is much lighter. It's the acceleration. So if I drop a piece of paper in a book, they should land at the same time, correct? Right. So in this case, the air resistance up is significant enough to counter its weight. All right. Does air resistance act on this? Yes. Well, yeah. Well, why doesn't it slow down? Yeah, it's bigger. Its mass is greater. So it's like, here's the piece of paper. Doesn't weigh much. But the air resistance is significant. Air. So the net difference is apparent. We're trying to keep that same scale here. Let's see. Let's say there's the same amount of air resistance on the book. It's about the same size. But the book weighs a lot more, so it hardly has an effect. Is there something I could do to the paper to make them land at the same time? Woo! Yeah, you eliminate that or minimize the air resistance, and you can do that. Just to save time here, let's grab this or this. Here's another fun way. What if you put the piece of paper underneath? Air resistance can't slow the paper down. They still hit at the same time. How about this one? They still land at the same time. Because the air can't get to the book. Air can't get to the paper. The book's blocking the air. So we got rid of air resistance. I'm going to do a demonstration for you on another day to remind you of this. Have you guys ever watched the video of the astronaut dropping a feather and a hammer on the moon? It's on YouTube. You should go watch it. It's on there. They did that. Well, we can do it here. Instead of taking you guys to the moon, I can put it in a vacuum and pull the air out to try to eliminate air resistance. And I'll drop a ball and a feather. And we'll see if what I'm telling you is a bunch of malarkey or not. So what is happening with this coffee filter? When I let go of it, it doesn't seem to accelerate for very far. You can see it starts at rest, it gets up to speed, but does it seem to go faster and faster? We mentioned this in a past class. What's happening? Yeah, terminal velocity. If the air resistance is less, can you see the net difference is small? But in which direction? The net difference is small, but in which direction? Down. So it still accelerates. At what rate? (9.8)? That's the acceleration due to gravity. But some air resistance is countering that. So the net force is not 9.8. It is it 0? So it's in between. What if, as it falls faster and faster, this increases? And at some point, if it balances and they're the same, now what's the net force? 0. The acceleration is, you weren't as confident on that one. If the net force is 0, the net acceleration is 0. And it no longer changes its velocity. That's terminal velocity. It's still falling. It's still going fast. Well, relatively speaking. A person would be going fast. But you're not going any faster. You're not going to speed up. You still don't want to hit the Earth going at that speed. We don't. Our terminal velocity is too quick for us to survive. But some small animals, flying squirrels and bugs, their terminal velocity is a lot smaller, a lot slower. And they can survive landing because they have enough air resistance on them to make their net acceleration 0. So they don't go any faster. Well, absolutely their mass contributes. We weigh a lot more massive than those examples I just gave, bugs and critters. So let's see. You saw those. Here's several of them. So the mass is increased. This is like the book. Now it's a much bigger down arrow. So for the same air resistance, it won't slow it down as much. Thus these fall a little faster. It still reached a terminal velocity. Could you tell that? But its terminal velocity is faster than just one coffee filter, because it took longer for the air resistance to counter its larger weight. So instead of being little arrows that are balanced, they have to be big arrows that are balanced. There's still terminal velocity, but you'll be going faster. Questions? Okay, who's ever skydived? I haven't yet. Is it fun? Or were you scared spitless? Did you reach terminal velocity? You're probably pretty high up, but does it feel like you're going really fast? When you open the parachute, what happens? Does it actually yank you up? Yeah, because that's a misnomer too. People think, oh, yeah, because it looks like that, because you're falling, the camera's falling with you. And if you all of a sudden increase the air resistance on you by opening your parachute, it doesn't like magically make you go upwards. It's just you start falling less fast. So it's like, oh. But meanwhile the camera is going, wah! So it looks like you got shot up. So the parachute just increases the air resistance and lowers your terminal velocity to a safe amount so you can land. I'll try it someday, but I haven't yet. All righty. We did it. That's all of Chapter 4. I'll start Chapter 5 next time. I wanted to make a couple comments and then let you go. One, on your homework, when there's a question that requires you to write out your answer, and most of them aren't that way, but I've stuck several in there, where it says like defend your answer, or why or why not. My purpose of doing so, again, is to get you to explain the physics. I want to see that you understand what's going on. Thus, we encourage you not to make little short blurb answers. If the question is, I don't know, doesn't matter, blah, 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 and it says defend your answer, and you just write, because of gravity. You're not showing me and the TA that you know what's going on. Reason it out. And it would be helpful if you wrote in full, complete sentences so we could follow your thought process. We reserve the right to deduct some points if we feel your defended answer is garbage. Most of the time we won't. I'm just trying to give you practice at explaining. But I want you to be aware of that. There was something else. Oh, there are 2, 4, 6, 8, 10, 11 of you that have not done the license activation process properly for clickers. If you were here today, I have your responses. Don't worry, I have them. But they're not necessarily assigned to you yet, and I definitely cannot upload them back to Canvas so that you can see until you have redeemed your license or verified your clicker or actually purchased the license and done so. So you might go check on your account. If you're curious if it's you, just email me. But it just tells me whether the license status is active or inactive. And 11 of you, it still says inactive. I still get your responses. I can see they're you, but I can't display them in Canvas for you to follow until you do that. And some of you also haven't registered a device number, so of course I don't know that you responded yet. I have several unassigned devices. Say you didn't register properly. You can still participate. I have those answers. I just don't know it's you yet, as an example. So just double check on if you're worried, on your turning account online, and make sure that it says you have a license and it says you have a clicker if you needed that. Because many of you are using ResponseWare. Okay, any last minute questions? I'm done. All right, see you Wednesday.